Texan Global School, Hyperbola. In this class, the equation of a hyperbola is analyzed. By definition, a hyperbola is the locus of a point in the plane, such that the absolute value of the difference of its distances from two fixed points in the plane, called foci, is always equal to a positive constant less than the distance between the fixed points. We can see that f and f' are the foci. L is the focal axis, which is the straight line that passes through the foci. V and V' are the vertices. The focal axis cuts the hyperbola at these 2 points. The distance between these points is the transverse axis, which is the portion of the focal axis included between the vertices. C is the center, located on the focal axis, which is the midpoint of the segment that joins the foci. Or it is also the midpoint between the vertices. L' is the normal axis, which is a line that passes through the center and is perpendicular to the focal axis. The conjugate axis is the portion of the normal axis between the points A and A'. A chord B and B' is a line segment that joins any 2 points of the hyperbola. E and E' is the focal chord which passes through one of the foci. The latus rectum, L and L', is a focal chord perpendicular to the focal axis. We see that the hyperbola has 2 latus rectums since it has 2 foci. A diameter D' is a chord that passes through the center. And FP is the radius vector, which is a line that joins the focus and any point of the hyperbola. We will obtain the first standard equation of the hyperbola. We will consider a hyperbola with center at the origin and focal axis coinciding with the x-axis. The foci f and f' are on the x-axis. These points can be defined as c, 0 and minus c, 0, c being a positive constant that represents the distance from the center to the focus. The vertices are the ends of the transverse axis, and they are at the points a, 0 and negative a, 0. Where A represents the length of the semi-transverse axis, and the ends of the conjugate axis are 0, B and 0, negative B. Where B represents the length of the conjugate semi-axis. If we define any point of the hyperbola, P of coordinates x, y, by definition of hyperbola, the absolute value of the difference in their distances to 2 fixed points on the plane called foci is always equal to a constant positive quantity and less than the distance between the foci. Algebraically, this definition can be expressed as the distance fp minus the distance f', p equal to plus minus 2a, where a is a positive constant less than c. By obtaining the distances between the foci and the defined point and substituting into this equation, results the square root of x minus c squared plus y squared minus the square root of x plus c squared plus y squared equals 2a. Following the same process as in the previous ellipse class, we obtain the relationship of b squared equal to c squared minus a squared. Be careful because the relationship is similar to that of the ellipse, but there is a variation in the signs. By substituting, we have x squared by b squared minus a squared by y squared equal to a squared by b squared. If we divide the entire equation by a squared b squared and simplify, results the simplest form of the equation of a hyperbola, called the first standard equation, or canonical form of a hyperbola, when its center is at the origin and its axes coincide with the coordinate axes. If we discuss this hyperbola equation, start with the intercepts with the axis. Let us remember that the intercepts with the x-axis are obtained when y is equal to 0. So the intersections with the x-axis are the vertices of the hyperbola, and the length of the transverse axis is the constant defined as 2a. Now the y-intercepts are obtained when x is equal to 0. However, in this case, there are no intersections with the y-axis since negative roots or imaginary numbers appear. The next point of discussion is symmetry. Symmetry about each axis is analyzed by substituting y with negative y and then x with negative x. In general, the hyperbola is symmetric with respect to both coordinate axes and also with respect to the origin. Now, to determine the extension of a curve, we isolate each variable and analyze for the determination of the variation intervals, for which x are real numbers, that is, the domain, by solving for y. So, the domain includes all real numbers less than or equal to negative a and greater than or equal to a. That is, values within the transverse axis are not included. And for the determination of the intervals of variation, for which y are real numbers range, by solving for x, we can see that the range includes all real numbers. For the asymptotes, we also analyze each value isolated. The hyperbola is not a closed curve. It has no vertical or horizontal asymptotes, but it has two oblique asymptotes. Using again the first standard equation of a hyperbola, from its foci, c is the abscissa. If we use the equation of the hyperbola, with the y isolated, to obtain the value of the ordinate, let us replace c with x. And using the previous relationship between a, b, and c, the ordinate is b squared over a. This value is the length of the ordinate or focus to a point of the hyperbola perpendicularly. Therefore, the length of the latus rectum will be twice that distance, as shown on the board. Finally, eccentricity is the measure of how much a conic section deviates from being circular. In a circle, the eccentricity is 0. Therefore, the eccentricity E is given by the ratio c over a, and using the same relationship between the variables, the eccentricity of the hyperbola is represented as the square root of a squared plus b squared over a. Contrary to the ellipse, this value must be greater than 1. Now consider a hyperbola whose center is at the origin, but its focal axis coincides with the y-axis. The foci f and f prime are on the y-axis, whose points can be defined as 0, c and 0, negative c, c being a positive constant that represents the distance from the center to the focus. The vertices, extremes of the longer side, are at 0, a and 0, negative a, and the ends of the conjugate axis are b, 0 and negative b, 0. With the same process, we find that the equation of the hyperbola is the same, but with the variables a and b inverted and a variation in the sign. The summary of the derived formulas is shown on the blackboard, which is very important to have on hand to solve the problems. The first standard equation of the hyperbola is shown, centered at the origin, as well as all the elements to be able to analyze it. And its asymptotes are obtained starting from the canonical form seen previously, solving for y. So if its abscissa increases at the points of the hyperbola, the radical tends to 1, then the equations are shown to obtain the asymptotes of the hyperbola. Let's look at an example. Find the equation of the hyperbola whose foci are the points 3, 0 and negative 3, 0. Its eccentricity is 3/2. Analyzing the given foci, we can see that they are located on the x-axis. Since the foci are at the coordinates c, 0 and negative c, 0, then we see that c is equal to 3. Hence, the midpoint between the foci is the origin. Using the formula to calculate the midpoint between 2 points, it is verified that the center of the hyperbola is at 0, 0. Now, because the given eccentricity is the ratio c over a, it is confirmed that c is equal to 3 and results that a is equal to 2. And since the vertices or extremes of the transverse side are at the coordinate a, 0 and negative a, 0, we can see that the vertices are at the coordinates 2, 0 and negative 2, 0. So since c and a are given, we can obtain b using the relationship between a, b, and c. By substituting and solving, results that b is equal to the square root of 5. Moreover, the ends of the conjugate axis given as 0, b and 0, negative b are in the coordinates 0, square root of 5 and 0, minus the square root of 5. With these values, results the equation of the hyperbola with center at the origin and focal axis on the x-axis, like x squared over 4 minus y squared over 5 equals 1. And by substituting these same values, results that the length of the latus rectum is 5. Likewise, we obtain the equations of the asymptotes according to the formulas derived and tabulate them to include them in the graph, proposing 2 points for each one. Finally, let us perform the tabulation with the equation of the hyperbola obtained to graph. First, solve for y and tabulate. The domain to propose values for the tabulation is obtained according to the ends of the transverse axis or vertices. So the domain is all those values less than negative 2 and greater than 2. Hence, obtain the tabulation and graph. So the ends are the vertices of the hyperbola according to the value of a equal to 2. If substitute values of x outside the domain between the vertices, a complex number will result, indicating that there is no graph. In this way, we can see the complete behavior of the hyperbola with all its elements. On the other hand, If the coordinate axes are moved to a new origin of coordinates h, k, the new parallel coordinate axes will be x prime and y prime, thus generating new coordinates. Then the transformation equations from the primitive system to the new coordinate system are x equals x prime plus h and y equals y prime plus k. Considering then a hyperbola with center at the origin and axis coinciding with the x-axis, let's perform a translation of coordinate axes. The coordinate axes can be moved parallel to a new origin h, k. The new parallel coordinate axes will be x prime and y prime, generating new coordinates. So, the equation of the hyperbola, referred to the new coordinate system, is shown on the blackboard. Performing the translation of coordinate axes, substituting, resuits the form of the equation of a hyperbola when its center is at the point h, k, and its focal axis parallel to one of the coordinate axes. This is the second standard equation of a hyperbola. Likewise, perform the translation to the equations of the asymptotes. The summary of the derived formulas is shown on the blackboard. We can see that the coordinates of the foci, vertices, and so on are specified according to the new origin h, k. The relationship between a, b, and c, the focal length and the constant quantity, the length of the latus rectum, and the eccentricity do not change. They are the same derived formulas. Let's look at another example. The vertices of a hyperbola are the points -1, 3 and 3, 3. Its eccentricity is 3/2. We will obtain the equation in standard form and graph. We can see that the vertices are not on the x-axis nor on the y-axis. Therefore, we will have a second standard equation of the hyperbola. As the vertices, or ends of the transverse side, are the given points, results that they are defined by the coordinates h plus a, k and h minus a, k. From these coordinates, results that k is equal to 3. Now, since the center is the midpoint between the vertices of the hyperbola, then the center is at point 1, 3. With this results the values of h and k. And since the given value of the eccentricity is 3/2, results that c is equal to 3 and a is equal to 2. Using the relationship between a, b, and c, substitute those values, obtaining that b is equal to the square root of 5. Since we already have the values of a, b, c, h, and k, calculate the ends of the conjugate axis, thus obtaining the points 1 plus the square root of 5, 3, and 1 minus the square root of 5, 3. Likewise, with these same values, we obtain the foci, -2, 3, and 4, 3. The length of the latus rectum is 5. Hence, the equation of the hyperbola with center at 1, 3 and axis parallel to the x-axis is x minus 1 squared over 4 minus y minus 3 squared over 5 equals 1. Substituting the calculated variables, we also obtain the equations of the asymptotes as shown on the blackboard. To graph, solve for y in the standard form and propose values to tabulate. The domain includes all real numbers less than -1 and greater than 3. We can see the behavior of the hyperbola with center at 3, 5, as well as all its calculated elements. On the other hand, the general form of the equation of a hyperbola can be found if we algebraically develop the second standard equation, as demonstrated in the last class and shown on the blackboard. Conversely, if we complete squares to the general form, the standard form is obtained. We will use the previous example to obtain the general and standard forms of the hyperbola, so develop algebraically by multiplying by the least common multiple of the denominators to eliminate them. In this case, multiply by 20. By multiplying each term by 20 on both sides of the equation, we see that denominators are eliminated, so develop the squared binomials and the products. By grouping, results the general form of the hyperbola equation. Conversely, using the same equation in general form, if we complete squares, results the standard form.
Texan Global School. Global online learning. Knowledge for the world. www.texanglobalschool.com